Okay, that just won't erase.
It would be really cool if a different one of us said that every morning.
Oh, I bring you in and do rotate it? That's nice. That's what you're think about that. Okay, so what did we do yesterday? Let's see. Oh yeah, we did separable differential equations, right? Separable first order differential equations. Right? We did. Yeah, that was the easy case. And I said it was just so easy, right? You could just separate things, integrate. You have to learn that one first. But after that, I don't want to start throwing just weird differential equations at you and saying, here's the technique. So instead, we want to get towards this thing called the Laplace transform. And you saw how excited Edgar was that we were doing this. Before we do that, I need to recall a couple of things from single variable calculus. You learn infinite series and improper integrals. So I'll give you the basic definitions for these things, maybe an example of each, and then the first homework, which is up now, you get some practice doing at least some improper integrals. Okay, and then once we get through that, we'll move on to the Laplace transform. So let's see, infinite series. So this is our next section, section 3. Infinite series, improper integrals. All right, so first, just a little bit of notation, which I'm sure you're all quite familiar with. If I write something like sigma over I equals 0 to n, then I'm really saying the sum. When I write ai, this means a0 plus a1 plus dot 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 to an. Right? Add up n terms of some sequence. Everybody remember that?
No.
Uh-oh. I have to send you back to first year calculus. Okay. Now, if I replace n with infinity, okay, then this sum doesn't stop. And I call this an infinite series. This was a finite series. Series just means sum of a sequence. So this is an infinite series. And we say that this infinite series equals a number L if you take this following sequence. It's a sequence where you only add up the first n numbers. So for the 0th term in the sequence, you just look at a0. And then the first term you look at a0 plus a1. And the next term is a0 plus a1 plus a2 and so forth. And that gives you a sequence of numbers. And if that sequence converges to L, then we say that the infinite series equals L. Or the sum is L. Okay. So there's one example that when you think of infinite series, you should always have in your head, the most important one. The most important. This is not a mathematical statement. This is just my opinion. The most important infinite series is the sum I equals 0 to infinity r to the I. Remember what this is called? Geometric series, exactly. So the nice thing about the geometric series is you actually know the value of it, at least if you have a condition on R. So the sum of the geometric series is actually just 1 over 1 minus R. You look really confused by that.
Is there any condition for R?
Absolutely. Is there any condition for R? What's the condition for R?
Greater than 1 less, greater than 0 less.
Greater than what?
0.
Greater than 0 and
Less
than 1. So you think it should be R between, like that? Is this too restrictive or is this perfect? For instance, could you put in 0?
Yeah.
Okay, so you can definitely put in 0. What if you put in negative numbers? Will those work? Like negative a half, say. So one thing you should remember is things, whenever you have these infinite series, there's this radius of convergence, right? It's always this nice symmetric circle, right? Well, it's actually just a line segment. The middle of the circle here is actually 0, which means it actually is going to go to minus 1 as well. So it should go minus 1 less than R less than 1, or alternatively, the absolute value of R is less than 1. So last semester in complex analysis, we used this geometric series all the time, right? All these Laurent series arguments we were using them. Okay. So this is important, of course. If you let R be 2, for instance, then you would have, let's see, 1 plus 2 plus 4 plus 8 plus 16 plus 32, and there's just no way that's going to converge to anything. But between minus 1 and 1, okay, it's okay to converge this. So for example, if you take the reciprocal of 2, 1/2, you raise that to the I, and this is kind of this, it's related to this famous problem of you walking from point A to point B, and to get there you first have to walk halfway. But then once you get halfway, before you can walk the rest of the way, you have to walk halfway. Of course, that's a quarter of the total distance. Then you have to walk another 1/8 of the way first, and then a 16th, and so forth. And this tells you actually will get there, because it's going to add up to 1 over 1 minus 1/2. And, well, 1 minus 1/2 is 1/2, 1 over 1/2 is 2. Okay. Well, the reason why you're getting 2 instead of 1, in terms of the problem I just stated, is that we're including the 0 term. If you started this at 1, you'd get to subtract 1. Okay, so this is useful all throughout mathematics, so you should know it. Okay, fine. Are there any questions about infinite series? That's all I really need you to know for right now. Okay, then let's talk about improper integrals. Okay, so recall again, well, something very easy, which is if, say, f of x is greater than or equal to 0 on some interval a, b, and say f of x is continuous on a, b. And the integral from a to b of f of x dx, what does this represent? It's the area, right? Area what? It's
bounded from A.
Yeah, you have some curve. You have A, and B, there's your f of x. And it's the area under the curve between A and B and above the x-axis. Area above the x-axis, beneath the curve, graph of f of x between x equals a and x equals b. What if I drop this restriction on greater than or equal to? So if I allow the function to go beneath the x-axis, well, then it's probably not giving me an area anymore. But you can still have the interpretation that it's canceling out areas, right? It's giving you areas above, positive areas and negative areas, and the answer you get is just you get when you cancel everything. Okay, so this is fine. All right, let me see. Maybe I won't go past there. Can you see over here okay? That I don't go over there. All right, so even if f of x is less than 0, we can still interpret the number as the net area. Okay, so net area meaning positives and negatives cancel out. Okay, if we let this b go to infinity, we can still consider the area under a curve. It's just going off to infinity. Fine. So you can write down this sort of symbol. And what we mean by this is the limit as b goes to infinity of these integrals that give you net area. So maybe you have some function that looks like this. And, okay, we'll put a right at the origin. And then you could start and put a b here. And then you could put another b called b prime, and that would give you all this stuff. And then you could put a, oh man, it was a green cat, but it just turned out to be a black cat. That's so sad. Okay, well. You can put a b double prime out here, right? And then you'll get all this area as well. Okay, so each time you choose some b, you get more and more area under this curve. And this symbol here, a to infinity f of x dx, is just saying take the limit as this b goes to infinity. So it's very similar to what we did with infinite series. When we said, okay, if you take an infinite series, you want it to equal L, that means you take, okay, it's like taking the limit here as n goes to infinity of these partial sums. So it's the same thing. Okay, so we call a integral from a to infinity f of x dx an improper integral. Okay, and then let's compute one just for old time's sake. So how about the integral from 0 to infinity of x to the p dx? Probably saw this at some point. Have to do something called the p-test. That's why they use p instead of some other exponent. Okay, so let's try to compute this. So by definition, this is the limit as b goes to infinity, integral from 0 to b, x to the p dx. Okay, now, if you just forget about this limit, you just want to compute this integral, this is pretty easy. You could use the power rule for it. Yep. So, leave this limit out front, and we get 1 over p plus 1 x to the p plus 1 evaluated at 0 and b. Stop me if you think I've made a mistake or an oversight. That's the hint.
If p is negative.
Okay, there's a problem here. If p is negative 1, I can't do this, right? Okay. So this is if p is not negative 1. What is it if p is negative 1? ln absolute value of x. Do I need to put the absolute value?
No.
No. Why don't I need the absolute value there?
X from 0 to...
Oh, you know what? I was just realizing here. This is actually going to be improper integral for two different reasons, right? In the p equals -1 case, and in a lot of these cases where p is negative, because of this 0. Let me make this a 1, just so that we don't have to worry about the behavior near 0. This won't hurt any. Just make things a little easier. Otherwise, we'll have to deal with things like 1 over 0. I don't want to deal with that. Okay, so if p is -1, you just have x to the -1, or 1 over x. Integral, right? It's going to be ln of x. Should be ln of absolute value of x, but since x is between 1 and infinity, we don't need the absolute values. So that's p. It's negative 1. Okay, so in the first case, we just plug b and 1 in. And let's see, we get 1 over p plus 1 times, okay, b to the p plus 1 minus 1 to the p plus 1. Minus 1. And in the second case, we get the limit as b goes to infinity, ln of b minus ln of 1. Okay, so now it's just a question of figuring out what happens as b goes to infinity. As b goes to infinity, what happens to this? If something going to infinity getting raised to the p plus 1.
So if p plus 1 is... if it is...
Ben says it goes to infinity.
But if it is negative, then it will go to 0.
Oh, yeah, so Ling says if the exponent is negative, then you have something going to 1 over infinity, so it's going to 0. So you need to figure out if this exponent is positive, then this thing's going to go to infinity. If the exponent is negative, then it's going to go to 0. So p plus 1 will be positive when p plus 1 is greater than 0, so p has to be greater than -1. So if p is greater than -1, then this thing is going to diverge. So remember the words we use when we talk about improper integrals. If you actually get a value, you say it converges. And if you don't get a value, you say it diverges. So it diverges if p is greater than 1. If p is less than I say greater than -1. If p is less than -1, then this will be negative, and it will converge. It'll go to 0. And so you'll get, well, this will be 0 minus 1. It'll be -1 times 1 over p plus 1. So minus 1 over p plus 1 if p is greater than -1. And what about if p equals -1?
P is less than.
P is less than...
Oh, less than, thank you. And if p is equal to -1, well, let's see here. Well, ln of 1 is easy. That's 0. As b goes to infinity, what happens to ln of b?
Goes to infinity.
Still goes to infinity, right? The graph looks like this. Okay, so it's still going to diverge even if it's equal to minus 1. So we can finish like that. Okay, so that's how we play with those things. No? You remember this? No? Okay, that's all I want to say about improper integrals. Just reminding ourselves. So now we can start talking about Laplace transforms. Ugh, terrible. Section 4, Laplace transform. All right, so let's let the AN be a sequence of real numbers. By the way, a sequence can be thought of as a function. Yeah? In what sense? What do I mean when I say that? It's a function from what to what? It's what's the domain? If I have a sequence like this, what is the domain? What does it eat?
0.
0 to infinity. Do you mean all real numbers from 0 to infinity?
Just all real numbers.
Just
So when I write down this notation, am I allowed to do something like a sub pi?
how numbers.
No, right, that's not what I mean when I use this notation. A sequence eats natural numbers, right, or possibly 0. So you could think of A as a function which eats a natural number, or 0, and spits out a real number. It's a sequence of real numbers. So if you had, say, 2, where would 2 go? It would go to A sub 2. Right? If you had 9, it goes to A sub 9. Okay, whatever that number is. So for instance, if my sequence, right, is 1/2 to the I equals 0 to infinity, okay, then, well, let me give a name, I'll still call it A. A of 0 is 1, A of 1 is 1/2, and A of 2 is 1/4, and so forth. And I could write this as A sub 0, and A sub 1, and A sub 2. So a sequence is just a way of taking this function notation that we're used to and shortening it up, getting rid of the parentheses, and moving the input down into the subscript. Yeah. So that sequences are actually nothing new. They're just functions whose inputs are natural numbers. Okay. So you have this nice sequence. And from every sequence, I can build a power series. Okay, so just remember, what's the power series? It looks like sum I equals 0 to infinity, some coefficients times x to the n. Okay, this is a power series, we might say about 0. So this is the power series. So if I start with any sequence, I can write down a power series whose coefficients are the terms of that sequence. Yeah. So for instance, let's say I have the following sequence. How about A sub n equals, how about 0 for all n? Right? The sequence is 0, 0, 0, 0, 0. I can write down a power series. This corresponds to the power series I equals 0 to infinity, 0 times x to the n. Well, I guess I should say I, not n. The index should match the exponent.
So it should be a sub I, x to the I?
Yeah, this should be an I also. Everything should be I if I do it like that. Okay, of course 0 times x to the I is always 0. So this is an infinite series that's going to converge to 0, because it's the sequence would look like 0, 0 plus 0, 0 plus 0 plus 0, and so forth. It's always 0. This is 0. Okay, that's not a terribly interesting one. Okay, what if I made it just slightly more interesting? We'll make it equal 1. Yeah? No, okay, this doesn't look much more interesting. But it is. Now you get, well, the coefficient is always just 1, so it's just x to the I. But this we've seen today. What is that? That's our geometric series, right? So the geometric series is just a special case, right, of this process of taking a sequence, namely the sequence whose coefficient, whose terms are all 1, and turning it into a power series. So we know that this is 1 over 1 minus x, at least when the absolute value of x is less than 1. Okay, so this is good. By the way, this shows, of course, that power series can, this one converges everywhere to 0. Doesn't matter what x's you put in. This one, of course, does not converge everywhere. It matters what x's you choose. All right, let me give you one more, and I see if you can figure out what it is. Third one will be a sub n is going to be 1 over n factorial for all n. Okay, so this gives you I equals 0 to infinity x to the I over I factorial. You know, if you stuck some Spanish words in there, it would look like an exclamatory sentence in Spanish. Okay, so what is this thing? What's it?
Is it something like a harmonic?
What is it? Say. I can't hear you.
Is it something with E?
Is it something with E? What is it with E? Does it help if I write out a few terms? Like I equals 0, you get 1 over 1. I equals 1, you get x over 1. I equals 2, you get x squared over 2 factorial plus x cubed over 3 factorial plus what is that? That's, yeah, you know what it is. Say it loud and proud.
Is it Taylor Swift?
E to the x.
Yeah, e to the x. Yep. Okay, so you start with this nice little input, you get out the function e to the x, right? You don't, you think, oh, here's a sequence. You don't think immediately, oh, e to the x, but yeah, sure enough, there's this nice, well-defined process. So this will be our first process, and we're going to call it a discrete transform. We're not going to use this anymore. I'm only doing it for comparative purposes. The reason why I call it discrete is because we're only using natural numbers as our inputs. Our next thing will be a continuous transform, where we allow all real numbers. So the discrete transform takes a sequence, a sub n, and it converts it into a power series. It's bad that I'm switching between i's and n's everywhere. So you're transforming a sequence into a power series. That's why I call it transform. It's transformation. Okay, so as I just said, I want to do a continuous version of this. So our second process is a continuous transform. Okay, but we're not going to call it that for long. We'll end up calling it a Laplace transform. So what should a continuous transform do? Well, remember the discrete transform eats a sequence. And a sequence is just a function whose inputs are the natural numbers. I want a continuous version, right? I don't want it to be just for here and here and here and here and here. I want it everywhere, right? Okay, so instead of putting in a function that only eats natural numbers, I'm going to put in a function that can eat real numbers. So let me call it f of t, because that's more usual notation for a continuous function. Okay, so f here is now a function that, well, I don't know what its domain is, but it sits inside the real numbers. And what am I going to do with it? Okay, well, I want to turn it into something that looks like this power series. Of course, a power series, I mean, you can't do that for every real number, right? When you do the summation notation, you're really just meaning for natural numbers. What symbol do I have to turn this into if I want to do all real numbers? Well, think back to what we started with. We started the day we talked about infinite series. That's when you add up an infinite number of these natural numbers, right? Or real numbers, but it's indexed by natural numbers. If you wanted to get something under a curve that took account of area for all real numbers, use integration. Right? Integration is what allows you to add up things that are indexed by the real numbers, not just by the natural numbers. Okay, so that tells us that instead of summing from 0 to infinity, we want to integrate from 0 to infinity. Then what we did here is we took the sequence and we made those coefficients of powers of x. We do the same thing here. Instead of the sequence, we take our function and we put it in front of x to the t. And we integrate with respect to t. So this is a continuous transform. This is one way you do it. And this is actually a rather useful sort of procedure in math, this idea of a transform. And it gets used in a lot of different places, and there's more than just the Laplace transform that we're going to talk about. There's the Fourier transform and various others. And I won't go too far into the theory of these things, but this is a useful thing to have in your mind that you can do. Now you might ask, well, why? What's going on, right? Well, when we see the Laplace transform, we'll give the best answer to that question. But go back to the discrete transform version. It is interesting to talk about sequences in their own right, but the process of turning it into a power series gives you something else really to talk about. And you can use tools that you know for power series to then say something about the original sequence. And we want to do the same thing here. We want to explore the original functions, or at least things that have to do with the original function, by exploring this transform. And you might think that this looks a lot worse. Just as a power series looks a lot worse. But it will actually make a lot of problems much simpler. And that's why we want to do this. So now it's going to turn out that what I wrote down over there is not the best form for doing calculations. You might think, well, there's nothing so bad here, right? F of t is, well, it's just some function. We don't know much about it. But x to the t is great, right? That's really fun to do things with. And you can imagine if you wanted to do this integral, what method is really going to be your bread and butter? See, two functions really, right? And you multiply them together. There's a product. Okay. What integration method did well with products?
Integration by parts.
Integration by parts. Yeah. Okay. So that sounds great. But it turns out that there's something just a little bit better than polynomials for integrating. What's just a little bit easier than integrating a polynomial?
Constant.
Well, constants are part of the polynomial class, and they are a little easier than a general polynomial, but there's something even a little bit easier than that. Exponentials, yeah, right? What's the integral of e to the x? E to the x, right? This is very nice. Plus c, of course. All right, so we're going to fiddle with the format of this integral so that we can get an exponential in there and make it a little easier to do calculations. All right, so let's take this transform and let's toss an exponential in there in a sort of nasty way. And before I do that, let me mention, I guess I can put it back over here. If x is positive, well, we don't really have a problem with positive, but if it's greater than 1, then what's going to happen as t grows?
It's going to grow exponentially.
It won't grow exponentially, but there will be polynomial growth because it's a polynomial. Okay, so this is going to grow very fast if x is greater than 1. And, well, it could be that f of t will cancel out some of that growth. All right, but you have to be very lucky for that to happen. Yeah? I mean, f of t would have to be, have to be going to 0 with exponentially. It would have to be something like e to the minus x, something like that, or minus t. But in any case, you have to get lucky, right? So to give ourselves the best chance of convergence. We assume that x is less than 1. Okay, now there's another problem with x. If x is negative, for instance, say x was negative 1, and t became, I don't know, 1/2. Then you would have to at some point evaluate minus 1 to the 1/2. What is minus 1 to the 1/2?
I.
All right, this is the square root of minus 1, right? This is I, but we're not really talking in the complex world in this part of the class. We will get back to it, though. Yeah, this is bad, right? You start taking square roots of negative numbers, you're in trouble. So let's also assume that x is greater than 0, so that we don't end up in that problem. So we'll start with that assumption. Okay, so to introduce e into this game, I play a really nasty trick. I write x as e to the ln of x. Of course, I'm allowed to do this. Can't stop. And of course, why am I really allowed to do this? Well, back over here, I said x is greater than 0. So ln of x makes sense. You might have asked, well, why did you make it greater than 0, not greater than or equal to 0? Because that certainly won't hurt you as far as convergence. But I knew that later on I want to make this transformation. So I better make ln of x defined by making x greater than 0. Okay, but this this is kind of nasty looking. This is certainly not looking a lot better. But let's see what's going on. So remember that, well, x is less than 1. And so what can I say about ln of x? If it's less than 1, well, let's see. ln of x, right? That looks like
Negative.
Yeah, right. Right there is where 1 hits it. So it's going to be negative. So this is less than 0. Okay. So I want to make something positive in there. So let me let, I'll say s be the negative of ln of x. So that s is positive. I can do that. Okay, so then ln of x is minus s, and so let me bracket that out. So we get that this is equal to the integral from 0 to infinity f of t e to the minus s, right? That's the ln of x minus s t dt. And then I'll just drop those parentheses. 0 to infinity f of t e to the minus st dt. So this is a reasonably natural thing to do here to make your equation look better. But here's the cool thing. Even though we set s equal to minus ln of x, we don't need to remember that. We just need to know that there is, well, this variable s here, and that s is greater than 0. That's what we said. And that's as far as we're going to go with this. We're going to call this right here the Laplace transform of f. Definition. The Laplace transform of f of t, and we'll call it L of f of t. So I use kind of a, I guess it's a kind of cursive L. And then my convention, and this is not, actually in the literature they like to use those curly braces, but I like the square brackets better here. L of f of t is defined as the improper integral 0 to infinity of f of t times e to the minus st dt. And as an aside, sometimes, once in a while, this notation is going to be too cumbersome for what we're doing, and we'll simplify and write this as f of s. Okay, now, there's actually something very interesting going on here. Note, when I had my discrete transform, if you start with a sequence, that's a function of n. Right? When you turn it, there it is, my transform. When you turn it into a power series, this is now a function of x. Right? This is one reason it's called a transform, is it's you change actually what it's a function of. You start with a function of n, and it turns into a function of x. And the same thing is happening over here with the Laplace transform. You start with a function of t, but when you integrate, you're integrating with respect to t here, so you're getting rid of the t's. But this s, that doesn't go away. You're not substituting any numbers in for it. So you start with a function of t, and you end up with a function of s. So this is not as good as transform. Don't confuse this with the antiderivative. This is not the same notation. But normally I'll use this notation, just once in a while. All right, so let's maybe do an example. And we'll do a few examples of these. That'll probably take us through the rest of the day, and then next week I'll show you what this has to do with differential equations. All right, what is the, I don't know if I number these. See if I number these. Yeah, okay. I'll call this 0 because I just wanted to end. Okay, this will be number 0. What is the easiest function you can imagine taking the Laplace transform of?
0?
Yeah, 0 definitely the easiest function you can think of. Okay.
Why am I always the one who
Okay, without having to think too hard, you can probably figure out what the answer is. What's the Laplace transform of 0? See, we've got to go to this definition here. Okay, you have to put 0 in here. Okay, so you're taking the integral of 0. It'd be 0. Okay. This one is not terribly interesting. Okay, so what's the next easiest function you can think of?
1.
No, 1. Okay. All right. Now, before I do this, let's just recall one thing. You can imagine why it's going to be important to know this. What's the antiderivative of e to the minus st? Ben can do this in his head. Negative 1 over s.
E to the negative s.
Yeah. And you think if you differentiate this, right, you have to use the chain rule. The derivative with respect to t is minus s, so that cancels with this. Okay, so we'll have to use that. All right, so the Laplace transform of 1, by definition, is the integral from 0 to infinity of 1, which I don't have to write, times e to the minus st dt. And now you can see it's already quite useful knowing this antiderivative. So this is going to be the limit as b goes to infinity of minus 1 over s e to the minus st evaluated at 0b. Okay, so well, let's see, this minus 1 over s I don't worry about, I'll pull that out. Okay, I get e to the minus sb. Remember, t was the integrating variable here, so that's where the b goes in for t. And then minus, when you put in a 0, this whole thing just becomes 1. Okay, so as b goes to infinity, what happens? Well, remember, s, we should say it again here, s greater than 0. Right? S is positive. So b is going to infinity, that's positive. S is positive, so you put a negative here, the whole thing is negative. It's going to negative infinity. So e to the negative sb is going to 0. So you're just getting 0 minus 1 is minus 1 times minus 1 over s equals 1 over s. So the Laplace transform of 1 is 1 over s. Okay. All right, so what do you think 2 is going to be? Well, see, 0 was the Laplace transform of 0. 1 is the Laplace transform of 1. So 2 is going to be the Laplace transform of
X.
Close. We'll use t.
Trying to trick us with a false pattern.
Yeah. You guys are getting too clever to fall for my tricks like that.
I've just been around you too long.
I know, I've torched you guys with that enough. I love the misdirection play. If you use it enough, then people know, they start to suspect the misdirection. All right, so by definition, this is the integral from 0 to infinity of t times e to the minus st dt. All right, what are we going to have to use to integrate this? Yeah, by parts. And of course, what am I going to want to use? All right, our table method, right? Yeah. Okay, so it occurs to me that there's a few of you who may not have seen this before. So if you've done integration by parts before, you know there's this u and a dv and a v and a du. I don't usually do it that way. I just make a little you just look like, what? There's no other way to do it, right? How can you not do it that way? All right, so let me show you how I do integration by parts. I just need a little space to do it on the side here.
Yeah, see, I learned this in math club last year.
Okay, now I'm not going to show you everything this method can do, but just enough to get us going. But this method is quite useful.
Really quite.
Here's just a typical example of something where you'd have to use integration by parts, and maybe even more than one time. I'm making an e to the minus x. Just make it nasty. Okay. So this is bad because you have to use integration by parts, but you can't just do it one time, right? You have to use it 2 times, and then you start running out of letters to call things. Here's what you do. You know that that's what you'd call your u, right? The x squared part. And that's what you're going to call your dv. So I put my u on one side, my dv on the other side, but I don't call them u and dv, I just write them down. Now I differentiate this until it goes to 0. 2x, 2, 0. Oh, that should be a minus x. Now I integrate this as many times as I differentiated x squared. So if I integrate, I get minus e to the minus x. Integrate again, I get e to the minus x. Integrate again, I get minus e to the minus x. I connect with diagonal lines, going down one step. Starting with plus, I alternate signs. Plus, minus, plus. The answer is then, I just read it across. X squared times, well, there's plus, so that's not going to do anything, times negative e to the minus x. So negative x squared e to the minus x minus 2x e to the minus x plus, and then minus is negative, minus 2e to the minus x plus. Okay, there's the answer. So this is much faster usually than setting up integration by parts like normal. But if you look at the method, I'm really doing the same thing as you did with these u's and dv's. I'm just getting rid of all that extraneous notation. I won't need any more right now, so I'll leave it like this. But later on, maybe I'll show you some other tricks you can do with it. And if you don't get it, just ask anybody in here who's had a class with me before that had any calculus in it. I can tell you all my tricks for putting boxes. And, yeah, that's Ben. He looks excited. So show you all sorts of stuff. Okay, so for this one, this is going to be quite easy. Okay, so we're going to put our t on one side and our e to the minus st on the other. We differentiate the t till you get to 0. 1 and 0. And then we integrate as many times as we differentiate it. All right, and as I said, it's very nice to know what the integral of this is. And sure enough, we have it. Don't have to remember. So this is minus 1 over s e to the minus st. And then if you do it again, well, you get the same thing, only you have to multiply by minus 1 over s. And so it becomes 1 over s squared e to the minus st. Draw our diagonal lines, plus, minus. Okay, and that tells us our answer. So we're going to get the limit as b goes to infinity of, well, let's see, let's make an observation. Each one of these has an e to the minus st in them, so we can factor that out. You have e to the minus st. And then what do you have here? Okay, minus 1 over s times t. So minus t over s. And then minus 1 times 1 over s squared. So minus 1 over s squared. Evaluated at 0 and b. Okay, so as b goes to infinity, what happens to e to the minus st?
Goes to 0.
That goes to 0. What happens to minus t over s?
Infinite. Negative.
It goes to negative infinity. Okay. Okay, so those are going to get multiplied. You're going to have one thing going to 0 and one thing going to minus infinity. Okay, we'll come back to that. Then over here, well, that just stays constant the whole time. So this times that is, well, that's going to 0 and that's constant, so that product must be going to 0. All right, so we're going to have to deal with what's happening when you have something going to 0 and something going to infinity. Then we use our old rule, right? If you have one thing going to 0 and one thing going to infinity, but one of them is exponential, right? That's the one going to 0, and one of them is polynomial, that's the one going to infinity. Who wins?
The exponential.
Exponential, right? Exponential beats out polynomials, polynomials beat out logarithms. They all go to infinity, right? But exponentials go fastest, polynomials go in the middle, logarithms go slowest. Okay, so that means since that's going to 0 and that's going to infinity, but that's exponential and that's just polynomial, that goes to 0. Okay, then you need to subtract what happens when you plug in 0. Okay, well when you plug in 0 here, that just goes to 1, no problem. This dies, and you're left with minus 1 over s squared. So in the end we get minus 1 over s squared, or 1 over s squared, with s greater than 0. Okay, so we might start making a chart of here. Right, so you have a function, and you have a Laplace transform. You know that if it's 0, you get 0. If you have 1, you get 1 over s, where s is greater than 0. And if it's t, you get 1 over s squared, where s is greater than 0. Would anybody like to guess what t squared will be? 1 over what?
I was going to say 1 over s to the 4th, but
1 over s to the 4th.
maybe
Any other guesses? What?
1/3.
S cubed? All right, let's. Who thinks it's 1 over s to the 4th? Not even two. Okay, you do. Okay, that's 1. Kaiway, you think so, or you're asking a question?
Kind of think so. I don't know.
Okay, what about 1 over s cubed? Who didn't vote? Does that mean you think it's something different, or you just don't know?
I just don't know.
Okay. Well, let's try it. We'll try it real fast. Okay, let's see. Well, we know we're going to... Well, okay, what is it? 0 to infinity, t squared e to the minus st dt. So we need to put a t squared and an e to the minus st. And we go 2t, 2, 0. Minus 1 over s e to the minus st. 1 over s squared e to the minus st. Minus 1 over s cubed e to the minus st. Plus, minus, plus. And so what do we get? Again, it's going to be the limit as b goes to infinity. Each one of these is going to have an e to the minus st. So pull that out. And we get t squared times minus 1 over s. So minus t squared over s. Then minus 2t over s squared. And then minus 2 over s cubed. And then we have to evaluate it, 0 and b. Okay, now it's actually the same argument as last time. As b goes to infinity, the e to the minus st goes to 0. And these two terms go to infinity, but only polynomial growth. Right? Well, they're going to minus infinity, but it doesn't matter. Right? Okay, so they get wiped out by the exponential going to 0. this thing is a constant, so it's going to 0. So all you care about is what happens when you plug in 0. When you plug in 0, this still goes to 1. This dies, and this dies, and so you're left with 2 over s cubed with a negative, but you subtracted it, so you get 2 over s cubed. So in fact, nobody was right. Now,
Okay. So then cubed.
well, what's t cubed going to be?
3 over s.
What is it going to be?
3 over
3 over s to the 4th. So that's the assertion. Okay.
6 over x to the 4th.
Okay, Christina says 6 over x to the 4th. Why 6
Oh,
over
yeah,
x to the
6.
4th?
Because it's not 2, it's 2 factorial. And that'll be
It
3
will be
factorial,
6.
and it'll be 4 factorial, because it's...
Yeah, you notice the argument is going to be the same every time, right? This is going to go, next time it'll be t cubed, 3t squared, 6t, 6, 0.
Right.
And the only term that's going to give you anything in the final answer is going to be this last term, right, from when you put in t equals 0. Because everything else is going to die when t goes to infinity because of that e to the minus st. All right, so this last term came from that 2, which is the last term here. But if you start with t to the cube, right, t cubed, the last term will be 3 factorial, or 6. So in fact, this is going to be 6 over s to the 4th. And what about t to the n for some natural number n?
Factorial.
N factorial over
s to the n plus 1.
s to the n plus 1. Exactly. Okay. So it almost works the way you think it should. But okay, it gets tweaked a little bit. You get a factorial in there. All right. So far, the only transforms we've done are the ones on the board, and they've all made what we started with slightly more difficult. Not a lot more difficult. Okay, they're reciprocals, which is not as nice. But since s is greater than 0, there's no discontinuities. They've raised the exponent by 1, right? T cubed became s to the 4th. Okay, and then maybe you get this extra constant in there. So they're not as easy, that's for sure. They're just a little harder, but not too much. All right, so next week we'll start by giving you an example of a function whose Laplace transform actually gets easier. And then we'll show what they have to do with differentiation and differential equations. Did you have a question?
I just wanted to talk to you.
Oh, okay. Okay, so why don't we stop right here then? That's a good place. Kind of fun.
Stop recording.